49 million years ago, crocodiles basked on the shores of the Arctic Ocean. Not metaphorically, not in some temperate refuge pocket. Actual crocodiles, alongside turtles and hippo-like mammals, lived where the North Pole sits today. The water temperature hovered around 13 degrees Celsius, roughly the same as the coast of San Francisco. Metasequoia forests lined the basin. There was no ice anywhere on Earth. Antarctica was green. Then a fern the size of a thumbtack grew across the surface of that Arctic Sea, and within 800,000 years, the planet had entered an ice age that persists today. The early Eocene was a hothouse. Atmospheric carbon dioxide sat at approximately 3,500 parts per million, more than 9 times current levels. The elevated CO2 traps infrared radiation that would otherwise escape to space. Ocean currents distribute heat globally. Polar regions received months of continuous summer sunlight with no winter ice to reflect it. The thermal gradient between the equator and the pole was shallow. The planet was uniformly warm, stable, and lush from pole to pole. This configuration had persisted for roughly 200 million years. Every dinosaur that ever lived saw a world without glaciers. Early mammals evolved in forests that extended to latitudes where tundra exists today. 6 million years before the Azolla Event, the planet experienced its most extreme heat spike, the Paleocene-Eocene thermal maximum. 55 million years ago, a massive carbon release drove global temperatures even higher, with palm trees in Alaska and crocodiles in the Canadian Arctic. The greenhouse state was self-reinforcing. High CO2 meant high temperatures. High temperatures meant increased evaporation. Water vapor is itself a potent greenhouse gas, trapping additional heat. Warm oceans released carbon back into the atmosphere, rather than absorbing it. The system resisted change. Breaking this cycle required removing carbon from the atmosphere faster than volcanic outgassing could replenish it. Chemical weathering of rocks slowly consumes CO2, but operates on timescales of tens of millions of years. The transition from greenhouse to icehouse happened far faster. Global temperatures began dropping around 49 million years ago. Atmospheric CO2 fell by an estimated 50 to 80% within roughly 800,000 years. By 34 million years ago, Antarctica was fully glaciated. No known geological process operates at the necessary speed. The rate of cooling requires a biological mechanism. Something alive had to pull carbon out of the air and prevent its return. The Arctic Ocean of the Eocene was nearly landlocked, enclosed by North America, Greenland, and Eurasia. Only narrow, shallow seaways connected it to the Atlantic. These passages were insufficient for deep water exchange. The cold, dense bottom currents that drive modern thermohaline circulation could not penetrate the basin. Water entered, but did not flush through. The basin functioned like an enormous enclosed lake. This isolation created stratification. The Eocene climate was hot and extraordinarily wet. Massive river systems drained the surrounding continents, pouring fresh water into the Arctic basin. With that water came dissolved minerals eroded from rocks, including phosphorus. Fresh water is less dense than salt water. The incoming river water spread across the surface and stayed there. Below it sat denser, saltier seawater. The two layers did not mix. This created a halocline, a sharp boundary between water masses of different salinities. The surface layer remained fresh enough to support freshwater organisms. Temperatures ranged from 10 to 13 degrees Celsius, comparable to coastal waters off San Francisco today. The water was warm, sunlit, and rich in nutrients. The shores were lined with metasequoia forests, dawn redwoods that thrived in the warm, wet climate. Fossil evidence shows turtles, crocodiles, and early hippo-like mammals at the North Pole. There was no sea ice. Summers brought 24 hours of continuous daylight. Below the halocline, conditions were entirely different. In a well-mixed ocean, wind and current action distribute oxygen from the surface to the depths. The stratified Arctic could not do this. The halocline acted as a barrier. Organic matter sinking from the surface consumed the limited oxygen available in the deep layer. Over time, the deep water became anoxic, depleted of dissolved oxygen. Without oxygen, aerobic decomposers could not function. The seafloor became a graveyard. Anything that sank into the deep layer settled onto the bottom and remained there, slowly buried under sediment. The carbon contained in that organic matter was removed from the active carbon cycle. It could not return to the atmosphere. Azolla is an aquatic fern adapted to life on still or slow-moving freshwater. Individual plants measure roughly a centimeter across. The structure is simple, a short stem, perhaps a few millimeters long, from which tiny overlapping leaves branch in a symmetrical pattern. The leaves are wedge-shaped, bright green on top, often reddish underneath, covered in fine hairs that trap air and help the plant float. Roots dangle below, hair-thin, absorbing nutrients directly from the water. From a distance, a mat of Azolla resembles moss or algae, a continuous green film covering the water's surface. It is common. In modern environments, Azolla grows in rice paddies across Southeast Asia, in ponds and ditches across Europe and North America, in wetlands and slow backwaters wherever conditions permit. Rice farmers cultivate it deliberately. The plant grows rapidly, smothers competing weeds, and then dies back. When plowed under, it decomposes and releases nitrogen into the soil, acting as what agricultural texts call green manure, a biological fertilizer. The practice is ancient, documented in Chinese agricultural manuals from over 1,000 years ago. The key to Azolla's rapid growth is symbiosis. Inside a small cavity in each leaf, nestled within the plant's tissue, lives a cyanobacterium called Anabaena azollae. The relationship is obligate. The bacterium cannot survive outside the fern, and the fern cannot grow without the bacterium. Anabaena performs nitrogen fixation. It captures inert nitrogen gas from the atmosphere and converts it into ammonia through a specialized enzyme called nitrogenase. The process is energetically expensive, requiring ATP generated through photosynthesis, but the payoff is enormous. Ammonia is a reactive compound that the fern can immediately incorporate into amino acids, proteins, and nucleic acids. Nitrogen is the building block of life. It makes up roughly 16% of all protein by mass. Most plants must obtain it from the soil or water in the form of nitrates or ammonium ions. These compounds are scarce in most environments. Availability limits growth. When nitrogen runs out, growth stops, regardless of how much sunlight, water, or carbon dioxide is available. Azolla has no such limitation. It manufactures its own nitrogen supply directly from the air, which is 78% nitrogen gas. The only nutrients it requires from the water are phosphorus, potassium, and trace minerals. Phosphorus is typically the limiting factor in freshwater ecosystems, but the Eocene Arctic had abundant phosphorus. Rivers draining the continents eroded rocks and carried dissolved phosphates into the basin. The supply was continuous. With nitrogen handled by symbiosis and phosphorus delivered by rivers, Azolla could grow as long as it had sunlight and carbon dioxide. Both were abundant. CO2 concentrations were 9 times higher than modern levels. The Arctic summer brought 24 hours of daylight for months. Under optimal conditions, warm water, high light, ample nutrients, Azolla doubles its biomass every 2 to 3 days. The mathematics of exponential growth become rapidly incomprehensible at human scales. Start with 1 square meter of Azolla on the first day of June. By June 22nd, 3 weeks in, you have 4,096 square meters, nearly an acre. By the end of June, 1 month after starting with a single square meter, you would have more than 500,000 square meters. That is 1 month. The Arctic summer lasts 4 months. By the end of August, assuming unlimited space and no constraints, that original square meter would have expanded to cover an area larger than several countries. The Eocene Arctic provided effectively unlimited space. The freshwater surface layer extended across the entire basin, millions of square kilometers. It provided unlimited nutrients through continuous river input. It provided warm temperatures, 10 to 13 degrees Celsius, warm enough for rapid metabolism and growth. It provided constant summer light with no darkness to interrupt photosynthesis. There were no herbivores adapted to feed on Azolla in significant numbers. There were no competing plants capable of matching its growth rate under those specific conditions. No other aquatic plant fixes its own nitrogen. No other freshwater plant can double every 2 to 3 days. Azolla bloomed. During the Arctic summer, continuous daylight and warm temperatures triggered explosive growth. Azolla spread across the freshwater surface, forming mats that could extend for thousands of kilometers. At peak coverage, the blooms likely spanned roughly 4 million square kilometers, an area half the size of the continental United States. The ferns pulled CO2 directly from the atmosphere through photosynthesis, incorporating the carbon into their tissues. They pulled nitrogen from the air via their bacterial symbionts. They pulled phosphorus from the water, continuously replenished by runoff. The system was self-sustaining as long as sunlight persisted. Then winter arrived. The Arctic plunged into months of darkness. Photosynthesis stopped. The massive floating mats, now starved of light, died simultaneously. Billions of tons of plant matter, saturated with water, dense with accumulated biomass, sank. In a normal aquatic system, bacteria, fungi, and bottom-dwelling organisms would consume the dead material, breaking it down and releasing its carbon back into the water as CO2. The carbon cycle would complete. But the Arctic seafloor was anoxic. Decomposers require oxygen. Without it, they cannot metabolize organic matter. The dead Azolla settled onto the bottom and remained there, chemically intact. Over time, pressure and burial began to compress it. The carbon was sequestered, removed from the active atmosphere. Then spring returned. The cycle began again. The process repeated for approximately 800,000 years. Each summer brought a new bloom. Each winter brought a new die-off. Each burial event removed another increment of carbon from the atmospheric reservoir. Estimates suggest the Azolla event reduced atmospheric CO2 from around 3,500 parts per million to somewhere between 650 and 1,000 parts per million, a drop of 50 to 80%. The exact figures remain debated, but the direction and magnitude are not. The Arctic Basin functioned as a planetary carbon sink, operating at a scale rarely seen in Earth's history. The mechanism was straightforward: photosynthesis without respiration. Plants pull CO2 from the atmosphere and use it to build carbohydrates, proteins, and structural tissue. The carbon is temporarily stored in living biomass. When the plant dies, decomposition reverses the process. Bacteria and fungi break down the organic matter, consuming oxygen and releasing CO2 back into the environment. The carbon cycles through the biosphere but does not leave it. The net effect on atmospheric CO2 is zero. Sequestration requires a second step: burial in an environment where decomposition cannot occur. The dead organic matter must be removed from contact with oxygen and deposited somewhere that prevents its return to the atmosphere. Peat bogs accomplish this on small scales. Swamp forests did it during the Carboniferous, creating the coal deposits that power modern industry. The Eocene Arctic did it on a continental scale. The seasonal cycle drove the process through 4 phases, repeating with mechanical regularity. During spring and summer, Azolla grew explosively under 24-hour daylight. The bloom spread across millions of square kilometers. The mats thickened, potentially meters deep in places, with older dead material compressed beneath fresh growth at the surface. Photosynthesis operated continuously. The biomass accumulated week after week, month after month. Then autumn arrived. Day length shortened. Light intensity dropped. By late autumn, the Arctic plunged into polar night, months of continuous darkness. Photosynthesis stopped completely. Without energy input, the plants could not maintain cellular functions. The massive floating mats, now starved of light, died simultaneously across the entire basin. There was no gradual decline, no partial survival. When the light disappeared, the bloom collapsed. Dead Azolla is waterlogged and dense. The air-filled cavities in the leaves that had kept the plants floating filled with water. It sank. Billions of tons of plant matter descended through the freshwater layer, through the salt water below, and settled onto the anoxic seafloor 3 to 4 kilometers beneath the surface. Under normal circumstances, bacteria and fungi would consume this material within weeks, returning its carbon to the water as CO2. The carbon cycle would be complete. But the Arctic seafloor was anoxic. Aerobic decomposers, the organisms that efficiently break down plant matter, require oxygen to metabolize organic compounds. Without it, they cannot function. Anaerobic bacteria can survive in oxygen-free environments, but their metabolic pathways are limited. The dead Azolla settled onto the bottom largely intact. Sediment from river runoff, fine clay, and silt particles drifted down and began to cover it. The weight of accumulating layers compressed the organic matter, squeezing out remaining water. Under pressure, and in the absence of oxygen, the plant tissue started the slow transformation into kerogen, a waxy, carbon-rich solid that is a precursor to petroleum and natural gas. Given enough time, heat, and pressure, kerogen matures into oil. The Azolla deposits in the Arctic are technically fossil fuel precursors. The carbon was locked away, removed from circulation. It could not return to the atmosphere. Then spring returned. The sun rose. Daylight increased. Surface water warmed. New Azolla spores germinated. The cycle began again. The bloom, the die-off, the descent, the burial. Year after year, decade after decade, century after century. The Arctic Basin functioned as an autonomous carbon sequestration device, running without supervision, without maintenance, without any feedback mechanism to regulate it. It simply existed, driven entirely by seasonal light cycles and the passive chemistry of stratified water. 800,000 years is geologically brief, less than 0.2% of Earth's age. On a graph of Earth's climate history spanning billions of years, the Azolla Event is a nearly vertical line. The speed matters. Climate systems have inertia. Oceans hold heat and release it slowly. But carbon dioxide is the primary control knob for Earth's temperature. It sets the baseline. High CO2 means high baseline temperatures. Low CO2 means low baseline temperatures. The relationship is not instantaneous. Oceans create thermal lag, but it is inexorable. As CO2 concentrations fell, the global energy budget shifted. Less infrared radiation was trapped. More escaped to space. The planet began to radiate away more heat than it received from the sun. Surface temperatures dropped. The poles responded first. They receive less solar energy per unit area than the equator, and during winter, they receive none at all. As atmospheric CO2 dropped and global temperatures declined, polar regions crossed a critical threshold. Snow that fell in winter began to survive the summer. Antarctica was the first to freeze. The continent sat over the South Pole, isolated from other land masses by the developing Southern Ocean. Snowfall accumulated in the highlands. Albedo feedback engaged. White snow reflects sunlight rather than absorbing it, which causes further cooling, which allows more snow to persist, which increases reflection. The feedback is self-reinforcing. By approximately 34 million years ago, Antarctica was fully glaciated. Permanent ice sheets covered the continent. Glaciers calved into the ocean, releasing icebergs. Geologists identify the onset of glaciation in marine sediment cores by the appearance of dropstones, rocks carried out to sea by icebergs and deposited on the ocean floor when the ice melted. Dropstones appear in the Southern Ocean for the first time at this boundary. The planet had entered icehouse mode. It has not left. Once ice sheets formed, they altered atmospheric and oceanic circulation patterns. Cold, dense water sinking around Antarctica drove the formation of the Antarctic Circumpolar Current, which thermally isolated the continent, preventing warm water from reaching it. The ice became permanent. The Azolla Event did not single-handedly cause Antarctica to freeze. Tectonic shifts also played a role, but the CO2 drawdown created the thermal conditions that allowed ice to nucleate in the first place. Without that initial cooling, snow would have melted each summer, and glaciation would not have begun. The direct evidence for the Azolla Event comes from a single sediment core retrieved in August 2004 during Integrated Ocean Drilling Program Expedition 302, the Arctic Coring Expedition, known as ASEX. The target was the Lomonosov Ridge, an underwater mountain range near the North Pole. The ridge accumulates sediment continuously, building an archive of Arctic history stretching back tens of millions of years. Climate models and carbon isotope records suggested something unusual had occurred around 49 million years ago. Atmospheric CO2 had dropped precipitously, but the mechanism remained unclear. Geologists needed physical evidence. The challenge was ice. The Lomonosov Ridge lies deep within the permanent ice pack. Ice flows drift continuously, driven by wind and current. If a moving ice floe strikes a drill string extending kilometers to the seafloor, it will snap the pipe instantly. The solution required 3 ships. The Sovietsky Soyuz, a Russian nuclear icebreaker, operated upstream, fracturing large ice floes into smaller fragments. The Odin, a Swedish icebreaker, worked closer, pulverizing those fragments into chunks small enough to deflect around a ship's hull. The Vidar Viking, the drill ship, held position in the cleared zone using computer-controlled thrusters. Progress was slow. Drilling proceeded in intervals between ice incursions. They reached the target depth and penetrated sediments from 49 million years ago. The cores came up in cylindrical sections. The sediment showed stripes, alternating dark and light layers repeating rhythmically down the core. The pattern was immediately striking. The crew nicknamed it the zebra core. Dark layers consisted of compressed organic matter, black to dark brown, rich in carbon. Light layers consisted of diatoms, single-celled algae with glass shells that live in marine environments. Palynological analysis, the study of microscopic pollen and spores, identified the organic layers. Researchers dissolved samples in acid, which destroys minerals but leaves organic structures intact. The samples were full of Azolla spores, intact and identifiable. Some preserved cellular detail is visible under the microscope. The density of organic material was startling. The dark layers were almost entirely composed of compressed, fossilized Azolla, packed so densely that individual plants were indistinguishable. The zebra pattern confirmed the cyclical nature of the blooms. Each dark layer represented a seasonal cycle: growth, die-off, and burial. Light layers represented intervals when the freshwater lid weakened, allowing marine organisms to colonize the surface. By counting layers and applying radiometric dating, the team estimated the blooms occurred episodically over approximately 800,000 years. The hypothesis now had ground truth. The Arctic had been a freshwater basin. Azolla had grown there in quantities sufficient to leave a geological signature visible 49 million years later. The carbon had been buried and preserved. The core proved it happened. Azolla still exists. It grows in ponds across Asia, Europe, and the Americas. It still doubles every few days under the right conditions. It still fixes nitrogen. It still sequesters carbon, temporarily. When it dies in modern environments, it decomposes normally. The carbon returns to the atmosphere. Researchers have noticed its potential. If you could grow Azolla at scale and then bury it in anoxic conditions, preventing decomposition, you would have a biological carbon capture system. Some proposals suggest cultivating it in controlled basins, harvesting it, and then burying it or converting it into biochar. The process is called BECCS, bioenergy with carbon capture and storage. The Azolla Event provides a proof of concept. It demonstrates that biological carbon sequestration can alter planetary climate. It also demonstrates the scale required. The Arctic blooms covered millions of square kilometers and ran for 800,000 years. Replicating even a fraction of that capacity would require industrial-scale infrastructure and ecological engineering far beyond current capability. The event was also self-terminating. Eventually, saltwater intruded into the basin, likely due to falling sea levels or the opening of a deeper connection to the Atlantic. Azolla cannot tolerate salinity. The blooms died, and the freshwater lid collapsed. The sequestration stopped. Any artificial system would face similar vulnerabilities. Ecosystems are dynamic. A project designed to run for millennia would encounter conditions its designers never anticipated. The deeper lesson is about sensitivity. The Azolla Event proves that Earth's climate can flip between stable states on timescales far shorter than geological norms. The transition from greenhouse to icehouse took less than 5 million years, with the most intense drawdown occurring in less than 1 million. We are currently running the process in reverse. Humans are extracting carbon that was buried over hundreds of millions of years, coal, oil, gas, and releasing it back into the atmosphere over the span of 2 centuries. Atmospheric CO2 has risen from 280 parts per million before the Industrial Revolution to over 420 parts per million today. At current rates, we will approach Eocene levels within a few centuries. The Azolla Event shows where that trajectory leads. Not immediately, not linearly, but eventually. High temperatures mean ice-free poles. Ice-free poles mean rising seas. The feedback that drove the planet into icehouse mode still exists. They also run backward. The fern didn't plan to freeze the world. It simply grew where conditions allowed and happened to disrupt a system that had been stable for eons. The disruption was irreversible. Antarctica is still frozen. The icehouse persists. We are also disrupting a stable system. Unlike Azolla, we understand what we are doing. The Arctic Basin no longer has a freshwater lid. The ice is melting. There are no more crocodiles.